All right, I think it's a time to start our second lecture today in the first session. So the next speaker is S Dani, who retired from TFR, and now he is in CBS DAE Center in Mumbai. He will talk on geodesics on the modular surface and continued fraction expansions of their endpoints. Over to Professor Dani. You unmute him now. It's okay.
Thank you, Professor Patil, for the introduction. Let me begin by expressing my best wishes to Ravi Kulkarni on the occasion of his 80th birthday, a rare occasion for many of us. And wishing him successful and fruitful future henceforth. Maybe we might call this the third inning. At 50, people call it the second inning, but now 80 is in the third inning. So all the best wishes, Ravi. So, and I thank the organizers for providing me this opportunity to say a few words on this occasion. I'm actually not very much in the area of geometry as such, but there have been things which have been related to geometry, and I've chosen such a topic for this occasion for the obvious reasons. And so let me begin by sharing my screen. Here it is. Yeah. The topic, as you see it on the screen, is geodesics on the modular surface and continued fraction expansions for of their endpoints. Now, I suppose the first part is something very familiar to, and in fact, perhaps something basic or elementary for the present audience. The second part also is kind of folklore and standard, but maybe not exactly from the perspective which I am going to need and provide to that one extent. Okay, so let me move on to the next page. Yeah. Now, on the modular structure, I'll soon from the next page, I'll have some diagrams, but for the moment, to give the first introduction, let's just use the diagram-less formulation. So we're going to talk of geodesics, and actually it would be convenient just to look at one side of a geodesic, and like we prefer, it's always the forward side. Forward geodesics on the modular surface, and so each of them have a certain endpoint, which is on the boundary. So modular and the hyperbolic plane has a boundary, and there is, for each geodesic essentially is represented by some geodesic in the hyperbolic plane, and hence it has an endpoint, and which is a real number. And the interesting part of the story is that there's quite an interesting interconnection between the geodesic behavior of the geodesic and the number theoretic, or specifically what one calls Diophantine properties of the real number, which stands for its endpoint. So, that's what it's about. And more specifically, the Diophantine properties that are involved are that we will be concerned with are actually reflected in the continued fraction expansions. Now, I'm sure all of you have some basic idea of what continued fraction expansions are, but I'm going to need a certain generalization, which I'll introduce when I come to that. So basically, the talk is going to say a few things about the interconnections between these two schema, these two streams of ideas. Okay, so a quick recap of what we're talking about. So the modular surface, as we all recognize, is the quotient of the upper half plane, which is what I have here, the x plus iy, where y is positive, and it's the quotient by this group, ESL2Z, very familiar one. I don't think I need to introduce the notation. And where if I take matrix, this is my notation for the matrix ABCD, that acts as AZ plus B upon CZ plus B. And a few things to check here that in fact, if you start with a point on the upper half plane, this will actually go into the upper half plane, etc. Those are counted standard things which we can assume. So there's an action, and there's a quotient, and the modular surface, as you recall, is something of the quotient. And there's a very pictorial way of thinking about it, which has been very classical. Here it is. This is your upper half plane. Now you look at this triangle, not by straight lines, but these are two vertical straight lines. Actually, rather than thinking of this as an analog of this straight line, let's think of all of these as circles. So vertical lines also you can think of as segments of a circle, where naturally we are sort of thinking of the Riemann sphere. So, so we have this triangle, which actually has the privilege of representing all the points in the quotient. So therefore, this quotient can actually be thought of as this triangle with the following identifications. You identify each point on the left-hand side here to the corresponding point at the corresponding height on the right-hand side, so that will make a cylinder with a hole, kind of peculiar hole there, but you glue it by identifying the points in which are reflected, which are same under the reflection. So it sort of, there will be no hole left here. So I don't need to say that. But remember, this is a non-compact surface which has a cusp, what we call it a cusp in the sense. And the word cusp comes from the fact that so as you go further and further, the points at horizontal distance, even if the distance can become close to 1, as much as 1, the actual distance in the surface is getting very small and small and small, because the metric there is not either dx squared plus dy squared or divided by y squared. So when y is large, the distance is very small. So it's actually getting more and more like a sharp cusp. That's the cusp. So that's the surface. And the geodesics on this, I'll not go into too much detail, but they are actually nothing but they are images of Euclidean semicircles. So like I'll not count them in advance, but so the geodesics on this modular. So first of all, geodesics on the upper half plane, they are going to be images of semicircles like this. Pardon my additional part doesn't exactly look semicircular, but it's meant to be the semicircle joining these 2 points with the midpoint somewhere here. So this is actually this is a geodesic, and if you do it with all the points as well, the points on the real line, as well as a point here and a point at infinity, so that will go straight vertically. So these are also geodesics. And it turns out that these objects account for all the geodesics in the hyperbolic plane. And since the metric on the modular surface comes from the upper half plane anyway, so the geodesics on this will actually be the images of that. So they will look like, so if you start from here and so the geodesic is going, the geodesic is, let's say, going like this. Then from this point, this point is same as this point, and the direction is same as that. It will go like that. So, and if it hits here, for instance, then this point is same as this point, and then it will correspondingly get reflected and proceed. So it look like a kind of jumble of arcs on this, which is I would not venture trying to draw too much part of it. I'm sure you will understand what that means. Now, these geodesics can have very complicated types. First of all, on the other hand, I should perhaps start with there can be very simple types of geodesics, and there can be more complicated and more complicated ones. The simple ones comes from the following picture. So if I have 2 points here, which are on the real line, let's say, which are say conjugate quadratic numbers, then let me and if then this if I take 2 conjugate quadratic numbers, then the geodesic corresponding to this pair can be seen by very simple calculations to be a periodic geodesic. The image of this thing in the modular surface is actually a periodic trajectory, and so it will that's a periodic trajectory. So these you can say are very simple. On the other hand, there are from any point, in fact, there will be almost all directions. It will turn out that as you follow this track, that will partially take just a few steps, will actually become dense in the modular surface. And then there are certain intermediate objects, which is what interests me to a large extent, and they have the property that they are neither periodic nor they are dense, but actually there is for each of them there is a certain level below which they lie. And what does it signify topologically? Now recall that the object here, the surface, has no hole in the bottom part. The only non-compactness of the surface arises from the fact that there is this crust. Now, if I avoid my trajectory going above a certain level, then it is something bounded in the surface. It doesn't go to the crust. So it is the third type of geodesic trajectories that I will be emphasizing more, the bounded trajectories. Okay, so that's the kind of variety that we are going to see. And so here, first of all, okay. And now, as I said, for each of the geodesic trajectories, there is a certain endpoint, and the thing that we are going to focus on is the endpoint vis-a-vis the behavior of this trajectory. Okay, so here are that's the first part. Now, complete trajectory, which I will not be dealing much with that, but it consists of the 2 sides, and then so correspondingly it will have 2 endpoints on the boundary. Now, the real numbers together with infinity, we are going to view as the boundary. So, single positive forward geodesic trajectory has 1 endpoint, and the full geodesic has 2 endpoints. Now, here is the correspondence that's kind of been very inspiring, not just for in the case of the modular surface, but large part of homogeneous spaces, etc. This kind of correspondence has evolved, but we will not be going into that. That's not a part of what I'm going to talk about today. So here, restricting to the modular surface, there are these interconnections, so to speak. So the positive trajectory is divergent, that namely it has no limit point on the surface, if and only if E is rational. Now, one thing I think what is written there, but I forgot to mention, is that the endpoint for a geodesic in the hyperbolic plane, the endpoint is something uniquely defined. But for geodesic trajectory on the modular surface, it sort of has many segments, right? Many representatives, and correspondingly. So this geodesic, for instance, is same as this geodesic as far as the modular surface is concerned. So therefore, the endpoint is defined only up to the equivalence under the action of PSL2Z. That's something we should keep in mind. So coming back to this correspondence, okay, divergence. When will we have notice that there is one obvious trajectory which has no limit point, which is going to infinity, namely something that is simply going vertically upward. Vertically upward is a forward geodesic trajectory, and that will never return. So, and in particular, it has no it has no limit points. It's a divergent trajectory, and its endpoint is infinity. But if you take other representatives of this, they will be the image of infinity under the action of the modular group consists of all rational points. So all those geodesics which end in power geodesics which end in rational points, they are divergent. And the statement says also that that the converse is also true. The divergence corresponds exactly to the number being rational. The second other simple kind of things that I record are the periodic and spiral geodesics. Now I already mentioned that if you had two conjugate quadratic numbers, then the geodesic joining them is something periodic. When you look at it in the modular surface. Now, if you have a forward geodesic which is asymptotic to that, so let's say this is something. This is a periodic geodesic, but I have another one which is coming to having is reaching the same endpoint, which will mean that the distance between these two, the corresponding points here, is actually going to infinity. So if this is periodic, this is actually spiraling towards that, spiraling towards that periodic geodesic. So once the spiraling occurs, it means that surely it is not going above us. There must be a certain level which must capture that. So these are going to be bounded geodesics, and the characterization in terms of the number turns out to be simply that the endpoint is a quadratic number. The endpoint is a quadratic, so if the geodesic is spiraling to a periodic geodesic, then the endpoint is quadratic surd and converse. So interestingly, both these parts hold. And okay, that is kind of more number theoretic or simple computational aspect of the algebraic checking. Now, the third property that I want to focus on is that gamma is bounded, that is, it's contained in a compact subset if and only if E is badly approximable number. Now, badly approximable numbers already come in any first course of number theory, but just to quickly recall, what it means is that the approximability is in terms of rational numbers, and what this is saying is that E is said to be badly approximable number if E minus P by Q is greater than delta by Q squared for a fixed delta, there exists delta, but for all rational numbers for which this denominator makes sense. So when this happens, the number is said to be badly approximable. Now, in terms of behavior of numbers, this is something exceptional. As one it turns out that almost all numbers are well approximable, which is the opposite of being badly approximable. So they form a set of measure zero, and similarly, one can see that the phenomenon of the forward geodesic trajectory being bounded is something exceptional. Nevertheless, it is still abundant in the sense that they are uncountable, and also the Hausdorff dimension. There are other ways like the Hausdorff dimension in terms of which they actually form a large collection. So this we have is the basic correspondence that I'd like you to keep in mind. We'll go further with that. Now, for this, a quick introduction to the number theoretic part. So now, extending the idea of fractions, we can make sense. I suppose most of you know be aware of this, and I need not say that, but just in case there are some of you who are seeing such a thing for the first time, here is the way I like to put it. So like we can write fractions, we can also write fraction expressions of this form, which are continued, what we call continued fractions. Now, what should such a thing mean? Just like in the case of infinite series, what it just means that if I can start, say, this gives me a such an expression that just like in a case of an infinite series, provides me this. So at this stage, so I just introduced one a naught. Then second stage, I have a naught plus 1 upon a1 plus something. But let's say I wait to add this, and so that will be my second steps. Up to here, this is some other rational number now. It is a naught plus 1 upon a1. Now I can go to the next step. So, and then I will have a naught plus 1 over a1 plus 1 over a2. And so on. So this, just like in the case of series, this tells us gives us a certain sequence of numbers, which in this case they happen to be rational, and limit of rational numbers, of course, need not be rational. But if such a thing, when you write such a sequence, if the limit exists, then you would rather think of this expression being a representation of that limit. So that's the idea of continued fractions briefly. So the corresponding, if the truncated, these are called truncated expressions. The corresponding rationals are also called convergents, and if they converge to a certain number, then you think of this as a continued fraction expansion of the number. So okay, so yeah, I think I have covered this part. So the basic idea of associating to such an expression to a certain number with the understanding and proviso that there's a limit, which is a real number. Yeah, okay. Now let me go forward. So as I said, we need to ensure that the limit exists. And in certain classical simple cases, it turns out to be automatic in some sense. So first of all, the most often talked of continued fractions, they're called the simple continued fractions, continued fraction expansions. And as you may recall, they're obtained by a very simple strategy. Given any real number t, you take away the largest integer that is less than or equal to that. So let's say a naught. Then the remaining part, the t1. So this t minus a naught now is the number less than 1. You invert it, that's a number greater than 1. And you can again do apply the same thing to t1. And even if you have not seen it before, you can convince yourself that that's the way you get such an expression. You will get a naught plus 1 over a1, etc., etc. And the emphasis here being that you are always taking away the largest integer less than or equal to t. Notice that if t happens to be rational, then at some point you are actually going to not being able to, you're going to get 0 in between, and then you are not going to invert it. So there is going to be a finite expression for a rational number. The same procedure leads to a finite expression of this form. So there is the simple continued fraction algorithm, which the properties that if it is if the number is rational, you get a finite expression in that form, and otherwise you can go on and actually converges to the number that you are working with. So this gives one way of associating with each number a continued fraction expansion. Now, as far as this simple continued fraction expansion is concerned, the Diophantine properties that we talked about again translate very well into in a natural way. And let me quickly recall what that is. T, of course, as we say, t is rational if and only if the expression is finite, that I already mentioned. Now T turns out to be a quadratic sort if and only if the continued fraction expansion is eventually periodic. What this means is that if you agree to ignore some part of the sequence, say up to m, then for the rest of them, there's a certain periodicity happening. So this is a very classical theorem of Lagrange's theorem, which gives you this dichotomy. So earlier I had showed listed interconnections only with respect to the Diophantine property as such, and now here we have purely in terms of the continued fraction, equal continued fraction expansion in this case. The third badly approximable number being badly approximable, it turns out to be exactly equivalent to the sequence an being bounded. So keep that in mind. We'll come back to this part once again. Now, this is not relevant to what I'm going to say further. As to complete the picture, let me also mention that in this case, the chord trajectory gamma will be dense if in the surface, if and only if the sequence an is generic in the following sense. So you have a sequence an, and now if you think of any block b1, b2, bk, this is a finite block. So given any block, if you find some string in the sequence which agrees with the block, and if this holds for every block, then the sequence is called generic. Now, for an untrained eye, it might look as something that's not going to happen, but actually it's something that happens almost always. So the set of such sequences, in fact, when you look at the corresponding real numbers, they form a set of full measure. These include, for instance, the question of notion of normal numbers, etc. So I will not go more into that. So, but there is a characterization in terms of the simple continued fraction expansion. Okay, so now we are going to go out of the comfort zone of the simple continued fraction expansion. After all, why should we always keep taking the largest integer away and look at the difference? So here is what I'm going to propose. So we can construct more general continued fraction expansions as follows. This is not the most general, but this is the step I want to emphasize. So let a0 be an integer such that the different, let's think only of irrational numbers, just for simplicity. One can do the same thing for rational numbers and see where somewhere you have to stop or something like that. But let's, for simplicity, restrict to irrational numbers. So let a0 be an integer such that t minus a0 is less than 1. Then I can, of course, take this t minus a, this has two possibilities. Of course, a0 will be bigger than t or a0 will be less than t. So now I take t minus a0 inverse. Now this is obviously this is not zero, and therefore it can be invertible. So this is some real number whose absolute value is bigger than 1. It could be positive or negative, but it doesn't matter. We don't really need to exclude the negative numbers. In fact, when we go to more the analogs of complex numbers, we actually have to avoid. I mean, we should not have restrictions about leaving out some numbers. Anyway, so I can take this, and then now this is a number, non-zero real number with absolute value greater than 1. I can therefore do the same thing that I did before. Take an integer which is within a distance less than 1 from there, and subtract and get the second step. And because of doing it in this fashion, you can convince yourself, I didn't want to spend too much time on that, you can convince yourself that it will again correspond to the continued fraction expansions of this form. So in this case, the difference that is the need to keep borne in mind is that these numbers may be positive or negative, whatever. The only thing that we know is that after the second stage, they are going to have absolute value greater than 1. Okay, so now in this case, it is no longer obvious that the continued fraction expansion is going to correspond to a certain real number in terms of that series converging. But through a careful analysis, actually, it is, I have proved it in one of my papers that this convergence holds not only in this real case, but even in the case of complex numbers, when there are more flexibility that takes place, happens. So this is something I have referred to as lazy continued fraction. So the lazy being corresponding to the part that at each stage, you are, so long as you find an integer within less than one, you go jump for that. You don't try to see which side you're looking at. So and corresponding to that, you get a continued fraction expansion. Now, so this is only for general knowledge. Actually, I'm going to talk about this.
I have a question. Complex continued fraction means the coefficients are complex?
Integers will be replaced by Gaussian integers or Eisenstein integers, or I mean some discrete subring.
Okay, thank you.
Yeah. So now let's specialize to this. Always choosing the closest integer to the left is the classical simple continued fraction. There's also another another what might seem a canonical thing to do. Is always choosing the closest integer, whether it is on the left or on the right. It's called the nearest integer continued fraction expansion, and the corresponding CFE is called the nearest integer CFE. It's also known as the Hurwitz continued fraction expansion because it was Adolf Hurwitz who in 1880s studied this kind of continued fraction expansion, not just for real numbers, but actually for complex numbers. So anyway, so this is another side remark. So curiously, though this may seem not very helpful, for any irrational number t, it's always possible to have a continued fraction expansion such that all the ANs, so after the first stage, are either 1 or 2. This is an interesting exercise for all of you, perhaps. I don't. So any real number t can admits a continued fraction expansion where and the entries after A0 are always plus or minus 1 or plus or minus 2. Okay, so that's purely kind of maybe recreational thing, will not help us more. So the preceding this observation in particular shows that well, of course, I can then no longer expect that analog of this thing, right? Badly approximable cannot correspond to bounded, because I even said that any number t has an expansion just consisting of just 1 or 2, so plus or minus. Okay, so therefore, when for looking for analogs of this with respect to other simple continued fraction expansions, we have to have more restrictions. And the possible conditions for on CFE, which for which the characterizations, especially 2 and 3, would hold, have been explored in some of the papers. Some with Noguera, some with Ojas Sahasrabudhe, was been one of my research students, and then some of my papers as well. So that's the overall general background. So so far, at least now, we have the simple CFE, we have the Hurwitz continued fraction expansion, and it turns out that I mean, those are the simple things that you can remember, but there is also in the background, there are also many continued fraction expansions that are lurking, and you can ask questions about them as well. So it's a picture. Now, before I go to going back to geometry, etc., here are some historical tidbits I would like to mention. The continued fraction algorithm, as you would recognize, is sort of close to related to the Euclidean algorithm, from the which one uses for finding GCD, etc. Each time you subtract the smaller one from the larger one, which corresponds to taking a multiple away of the smaller one, etc. So that, and the particular algorithm, interestingly, for this sequence of convergence, they're actually known to to approximate. We know that they converge to the given number. They are approximates, but it turns out that even for rational numbers, it's a way of getting a good. If you have two. Okay, let me state it, recall it in the form that I have written it here. In India, the process of mutual division was also used for finding of for a fraction p by q with large p and q, a fraction little p by little q with smaller integers, which is sufficiently close to that. And that this is simply the fact that in the case of irrationals, the convergents are going to that. And so even for, if you take a rational number of this form and do its continuous fraction expansion, as you go to, so the original expression may have may be a long string, but these ones, the truncated ones are going towards that, so they are approximating that. And these approximations were actually used by, this kind of approximation was used by the Kerala astronomers in their practice of astronomy, because there's very often in astronomical calculations, you have to multiply by rational numbers which have to do with astronomical bodies, and then the correspondingly astronomically large numbers. And to reduce the pain of doing that, you would rather to have smaller fractions, which are simple looking fractions, which nevertheless would keep the error within some margin. So, and this was effectively used in many contexts. Interestingly, this was not done only with respect to the continued simple continued fraction, but also with respect to what we call the Hurwitz continued fraction. So in other words, you take given the rational number, you would find do the mutual division, not necessarily staying on the same side. Mutual division you do depending on what give you the next remainder to be smaller. So you can have the corresponding analogical continued fraction expansion of this. So, and mutual division in which you are allowed to switch sides. And this is seen to have been noted, though in a limited context of rational numbers. So of course, they were not talking about irrational numbers. In the well-known work Karana Paddhati by Uttamana Somayaji, this is the Kerala mathematician from the 16th, 17th century. And this method, this has been discussed in a recent paper of Venkateshwar Pai and M.S. Sriram. So there's just a historical digression to highlight which in particular highlights the significance of continued fraction expansions. So perhaps with more continued fraction expansions could perhaps do better, and I don't think that line has been explored. Okay, so now the remaining part I'd like to say about the geometric way of looking at the issue of boundedness. I mean, after all, you're talking about a certain trajectory. So you should be able to say purely in geometric terms when it is bounded or not. Right? How does it relate to the endpoint? That is, ultimately, I want to know want you to tell me in terms of the endpoint, but maybe you can just tell me in terms of the trajectory, given the trajectory. So let's analyze it in that fashion. So, okay, and for this, I'll largely focus on using the Hurwitz continued fraction expansion, which is something that I've adopted for various purposes. And so, though similar things can be done for the simple continued fraction expansion, as well as the more general versions. So, to an extent, not everything is going to be amenable to this, but with some restrictions that will sort of depend on the context and are technical, which will not go into that. So we are going to think of the Hurwitz continued fraction expansion as something of a prototype of a more general continued fraction expansion that interests us. Okay, so now as recall that we are interested in looking at various trajectories. So here is a picture I'd like you to bear in mind. So now my triangle has I've shrunk the triangle here. This is my modular surface triangle, I can think of I'm starting thinking of forward geodesics, and I might as well think of starting them from some point here, which is a good reference point, line. So the geodesic, from any point, if you take geodesics in all directions, that they actually cover everything. So if that's all you really need to understand, then you simply can shift the point, etc. So now, if I start with a geodesic, let's say it's moving in this direction, then I want to think of, and of course, then it's going forward, etc. From here, etc. That we know. But in the meantime, of course, it has also crossed several of these vertical lines, which I want to ignore. Okay, so given the positive geodesics, just with respect to this fundamental domain, there are little pieces of which it consists of. But I want to make a distinction when it actually comes to any one of these arcs. Okay, and so this is my one segment. From here, the trajectory, this point is then same as this point, and then say here the trajectory was going downward. So here the picture will go downward here, but this is same as. This point is same as this point by the flip, and therefore the trajectory will then look like it's going here, and so on. So I can keep doing this, but the point I want to emphasize is that I can keep track of the number of this. This is some this giving me a certain number. If this corresponds to 0, this corresponds to a certain number here. This is, notice that these distances are 1. So these arc bits correspond 1 to an integer. So this number I can also see. Then second time, I'm following it up that trajectory. So second time, during this 0 thing, it went to here it's a negative, but it could also be positive. So there is a certain next number. So this gives me a sequence of numbers which associated with each trajectory. And notice that it's quite obvious that if this sequence of numbers is bounded, then the trajectory has to be bounded, and conversely. Why? Because the trajectory here, what you see as the height of this is closely related, is actually just the diameter of this semicircle, and therefore this is sort of close to. It's not exactly that, but you can see that if this thing is going to be very large, this thing has to be also to be very large. So dramatically, it is now obvious that then a sequence of numbers that I associated with this being bounded exactly tells me that the geodesic is bounded or not, depending on this sequence. Well, so it looks like yes. So this is why doesn't this already give me everything that I want? So the catch is this is not exactly the sequence of continued fraction expansions for anything. Of course, you can introduce a geometric notion which has not been studied, but here is the way of looking at it, geometrically associating a certain sequence. And if this, if boundedness of this were to tell me about the boundedness of the continued fraction expansion of this, that would be great. That's all I would seek for what I was explaining there. But the catch is, so here this number doesn't exactly correspond to. So this trajectory goes further. Okay. So the number that you're going to choose is going to depend on this. Whereas here you may have the arc here, they correspond to this would be something different. So if the endpoint is here and then it's in the segment corresponding to this, and then the number that would be associated, because of the fact that this thing is still moving forward, the number that you associate for the geometric algorithm that I introduced, and what would turn out as the corresponding integer part of this though they look very close, they are not same. The problem is, they might actually, here you see that it will actually differ at most by 1. But that one difference of 1 turns out to be damaging, because depending on whether what you do at this stage, the things in the subsequent thing, what you're going to choose subsequently is going to be different. So the and what you therefore need is to be able to resolve this problem, and somehow try to patch up between the two sequences. Now, I thought I had another picture where there's a diagram corresponding to that, but that seems to have got erased. Okay, so yeah. Now, therefore, what we want to do is the following. Yeah, it's here. I'm sorry. Okay, so initially we were looking at these arc segments, each corresponding to one integer. Okay, and look at where your geodesic fell. But instead, what we would like to, we should do is to extend these arcs. Each of these arcs you extend a little bit. How much I'll come to that later. Think of extending these arcs a little bit on either side, and and you'd like to do it in such a way that when your trajectory goes forward and is going to correspond to the next one here, okay, your trajectory is it comes here and is ending up here, because of the endpoint, your preferred arc will be this one, right? Whereas the geometric picture is showing you this as the number. But then what you do is you ensure that you are thickening, you are elongating these arcs is such that you can go up to here and count that as the corresponding number. So purely by instead of thinking of these arc segments as segments, but think of the new sequence of arc segments and associate your coefficients corresponding to that. So that's basically the idea. So now, first of all, one has to find what exactly is the number, extent to which you need to extend, and that corresponds to what is called reduction of the continued fraction expansions, which I'll not go into for want of time. So therefore we thus have yeah. So that tells you a way of putting this geometric sequence into the number in connection correspondence with first for modifying the geometric sequence by thickening these arguments and identifying that to be the continued fraction expansions, you get a way of concluding the criterion 3, correspondence 3 that I talked about. Okay, so now one of the reasons, this is of course about the boundedness, and one of the reasons why one is interested in these trajectories being bounded has to do with the following problem. There's been a lot of study about values of quadratic form. So look at a quadratic form here, just a binary quadratic form, which is a product of two linear forms, A, B, C, D are integers, and you can also take the determinant to be 1. And you would like to know the number of integer solutions xy such that qxy is less than epsilon, and the norm of xy is less than n. So in other words, you want to count you want to take this kind of hyperbolic region and count the number of solutions within this. And it turns out that this is closely related to the trajectory getting up. First of all, the problem itself connects to trajectories of the geodesic flow, and then the number of the solutions corresponds to is stand connected with the number of visits to parts to certain level of the cusp. So the point is, whenever when so the diagonal group, which is what acts on the hyperbolic plane, that also acts in this R2. And when the trajectory is coming close to zero here, in the corresponding picture in the hyperbolic geometry, it's actually going to great heights. So that is something sort of incorporated in the Mahler criterion in the general situation, but here, of course, it's something very simple by calculation. Okay, so I'll skip this part because we're already run out of time. But this is roughly what I said. We have two actions of the diagonal group, one corresponding to the geodesic flow and acting on the upper half plane of the hyperbolic hyperbolic plane, and the usual plane, and the relation between them gives you a relation between these two. And so via that analysis and the correspondence that I mentioned in one of the papers, with Manoj Chaudhary, they proved the following. You take the quadratic form as I explained above, and now say A, B, C, D, B not equal to 0. Look at the sequence of the Hurwitz conductive fractions of A by B. Now, there's a kind of symmetrical, let me just look at A by B. And so look at these two numbers, lim inf and lim su. Okay. And suppose that this is positive and this is finite. Then the I give the following conditions. There exists constant so that so given epsilon and this kappa will see where it comes. There exists C minus and C plus such that for all sufficiently large numbers n, the number of primitive integral solutions of these inequalities, qxy less than epsilon, and kappa is chosen so to ensure that with this part large enough. So less than n. So this is so in other words, we are looking at, so we want the number of integer points in these tentacles. So we can split that part into four tentacles and look at them individually. That's roughly what we are doing. So, and that number, it turns out to be, this number of solutions turns out to be between C minus log n and C plus log n. Now, this is for quadratic forms. The corresponding thing for higher the higher order forms, ternary and all, is actually the part of the Oppenheim conjecture on which for which there's a separate theory which will not go into, and this in a sort of way complements what happens in the binary case, which had to be excluded there for various group theoretic reasons. So with this, I conclude, and thank you all for your patience, and thank the organizers for this opportunity.
Thank you, Professor Dani, for the interesting talk. Let's thank Professor Dani for his talk, and I would like to ask the participants if they have any questions.
Yeah, so I have a question.
Yeah.
So it is again related to that complex case that you talked about, your result.
Complex case.
Continued fraction. Okay. Yeah. So it is, yeah, here I think. Yeah, right. So my question is that whether you can generate generalize this theorem also to the quaternionic Gaussian integers? Is it make
No, I'm afraid I don't know. I not looked into it. I mean,
does it
there's
make
a whole lot of issues here which I mean, beg for being extended, etc. But I mean, it's kind of I have not done that. Yeah.
so one can generalize the definition, right? I mean, over
Yeah,
quaternion.
generalization makes sense. Yes. Whether it is true, I don't know.
Okay. Thank you.
Yeah.
Any more questions from the participants? I would also ask Professor Kulkarni to share his comments. I invite him to here.
Yeah,
Hello,
you know,
Ravi. Happy birthday to you in advance. Yeah.
thank you. This group action on geodesics, in general, if a group G is acting on a set X,
Oh.
then it starts acting on X cross X,
Oh.
X cross X cross X,
Yeah.
and so on. So if you take your G to be PSL2Z and X to be the circle, roughly, circle being parameterized by real and infinity, then your action on geodesics is the same as the action on X cross X.
Yeah.
Similarly, you have higher actions also, X cross X cross X.
No, they will split. They will not be.
They will not be transitive or something.
They will not be transitive. Yeah.
Yeah, there
I
will
mean,
be some.
they will. Yeah, they will not even be topologically transitive. I mean, they will not be dense objects.
Right.
Yeah.
But then there are other invariants there.
Yeah. Right.
Yeah, and somehow the original connection with number theory, somehow these are weak invariants when you go to these.
No, the corresponding number theoretic object has to be of higher dimension correspondingly. So SLNZ you have to take.
No. I'm taking PSL2Z.
Yeah.
And acting on my X is the
Projective
boundaries,
yeah.
the circle. Yeah.
Yeah.
And I'm just acting on X cross X, X cross X cross X.
Yeah.
Just the component actions. Somehow, can these actions be related to each other, or have you explored this such an idea?
No. Usual strategy is to split into components, but of course the components each time could be different. So that, I mean, whether given a certain, say, large n-tuple or something of real numbers, you might perhaps want what the corresponding segment of that is, but I don't know if you have seen that.
All right.
Yeah.
Are there more questions or comments from the audience? If not, let us thank Professor Dani once again. Thank you very much for that.
Thank you all.
And we will end this session and we'll resume at 4:30 for the next lecture. Thank you.